Aigi nungsizaraba mahiroi pumnamak, my dear students. Lockdown manung asida mayapunamak yumda lengdana libiramuni haina kalli. World Health Organization na piribesing adu ngakna sa piramuni haina kalli. Mamangda we have discussed about the Fourier transform of the rectangular function or the rect function, and we have also seen that the Fourier transform of a rect function is a sinc function. I am just repeating. This is the general definition of the Fourier transform, and it was found to be sinc function, sinc of S. This was the typical triangle function, and the Fourier transform of this triangle function was found to be Fourier transform of a triangle function was sinc square. Sinc square is, I'm just writing, Fourier transform of a rect function, rectangular function, was found to be sinc of that function, sinc S. So it's no accident that the Fourier transform of the triangle function turns out to be the square of the Fourier transform of the rectangular function. This is sinc and this is sinc square. This was the rectangular function transforming to, this has been transformed into sinc function. Like this. This is the sinc function, positive as well as negative. And this is the transformation of the rect function by to the sinc function by Fourier transform. This is Fourier transform of pi of S. Pi of S. Now, for the triangle function, positive 1 and this is negative 1, somewhere here is 0, then this is minus half, and this somewhere is positive half, and like that. And this is the triangle function. After taking the Fourier transform of this triangle function, it will look like then like this, then this, then automatically fading off. And you see there is no such negative portion in the case of the triangle function. This is your sinc square. Sinc square. This is your sinc, and this is your triangle function. Lambda of t or lambda of S, whatever. This is pi of t. So this we have discussed in the last classes. Now we'll be coming to exponential decay function, which is also commonly seen in the decaying and the growth of the electric current in the LR circuit or the LCR circuit, as you have already discussed in the B.Sc classes. LCR circuit is switched on. There is a growth of the electric current due to the electromagnetic induction, and when the key is open or it is switched off, the circuit is switched off. In that case, there is the current in the LCR circuit is not directly to 0, but it is just decreasing exponentially. It is not abruptly decaying to 0, but it is exponentially decaying. And such type of representation will look like this. It is just decaying like this. And this is the so-called exponential decay. And the function corresponding to this ft will be known as the exponential decay function. And what happens if we take the Fourier transform of this exponential function, and you see this a positive constant, right? And this function models a signal that is 0 when it is just switched on, and then it begins to decay exponentially as shown in the figure. And this figure will represent the graphs for some 1.51 or 0.5, 0.25 and like that, some of the typical decaying phenomenon that we can see here like that. It is just these are meeting at the points lying at infinity, but forget about all these things. If I take the Fourier transform of this function, the decay function, then what will look like Fourier transform plus infinity, then e power minus 2 pi I s t, then f of t, then this is dt. This is Fourier transform of the function. Now, from the limiting portions from 0 to infinity, what happens actually, this will be e power minus 2 pi I s t, okay, then e power minus a t, then this is dt. So I'm not putting the 0 part, I'm just taking this part, e power minus a t, f, the function ft will be equal to e power minus a t when t greater than 0 in the sense it lies between 0 to infinity. So integration over 0 to infinity e power minus 2 pi I s t, by definition, and f of t, this f of t is replaced by this e power minus a t under the condition that t greater than 0. So for the points when t less than or equal to 0, these are 0, so I'm not putting that part. This is how we write out the Fourier transform of the function. Now, what will it look like? This will look like this 0 to infinity. This is e power something and this is also e power something. Base remains the same. So I can write this in the form e power minus 2 pi I s t, then this is minus a t, okay, then this is dt. So further this will be equal to 0 to infinity integral, then e power minus, I can take t as common, so 2 pi I s, this is some sort of thing like this, dt. Okay, now this is of the form integration of 0 to infinity e power a t again. So this represents, this whole sum will represent a, which is an standard integral. What is that? E power minus 2 pi I s, then minus a whole into t, then it will be divided by the quantity, the differentiation of this quantity. The differentiation of this quantity is minus 2 pi I s, then minus a. So I write this as the, now after this, just let us just write, which is equal to e power whole into t divided by minus 2 pi I s minus a. Then what remains will be e power, this is minus a t. So this is e power minus a, then this is under the limit t, which is equal to infinity. Now what about the other component? The other component is e power minus, this is minus 2 pi I s, then a times t divided by minus 2 pi I s minus a, then limits of integration here is for t equal to 0. Then if I put the limits, then what will happen? This will look like e power minus infinity, the first part, and second part is e power 0. So e power 0 is 1. This part will be equal to 0. Then what about this? E power, in place of t, if I write 0, then e power 0 is 1. So minus 1, this is minus 1 divided by, then the denominator will be minus of 2 pi I is minus a. And this is of course some sort of 1 by 2 pi I s plus a. If I take minus s common, then this will be plus. If I take minus s common, this will be plus, and minus minus getting cancelled, so 1. And this part will be equal to 0. So this is how we take the Fourier transform of the decay function. So now it is very clear that unlike the results of the rectangular function, as we have discussed earlier, results of the rectangular function as well as the triangle function, the Fourier transform is very complex. Rectangular function and triangle function are real because their functions are even, and here in this case the function is not even, and power spectrum for this result, therefore the power spectrum will be given by power spectrum is given by the square of the Fourier transform. So f of s, this is whole square, this gives the value of power, and this power will ultimately be equal to 2 pi I s plus a, this square, and then this will be 1 upon 2 pi I s whole square. Okay, this whole square will be I square will be minus 1 again, so 2 square will be 4. So ultimately I can write this as I'm just writing the positive quantity first, a square plus then this will be 4 pi square, then s square. I square was equal to, square of I was equal to minus 1, and it has been cancelled. So this is the power spectrum. So power of the spectrum will be given by 1 upon a square plus 4 pi square s square, and the final spectrum will look like this. This was the spectrum for the decay function. This is the decay function, and this will be transformed into this, some sort of thing like then this will go off straight, very sharp, and then this will be decaying like this, and in between there are also some small peaks, not so high, like this, and then like that, and this is not actually the Gaussian function. It looks like the Gaussian function, but it is not so. This is the so-called Lorentz profile, and it is the shape of the bell curve. The Gaussian function was given by this, was the Gaussian function will be like this, some sort of, then like that. So this is Gaussian, and this is it looks, the main peak looks like the Gaussian, but it is not so. Fourier transform of the triangle function, and this is the Fourier transform of the decay function, which is the so-called the power spectrum, and this is your f of s whole square power spectrum, and this is Lorentz profile, or Lorentz profile. So I think all of you have understood well this discussion, the Fourier transform of the decay function. Decay function, as you see, decay function is some sort of function which decays with the passage of time. So Fourier transform of a decay function is found to be a Lorentz profile, which is given in the figure like this. Very simple calculations. I think in between there is no doubt. If you have any doubt, sometimes we also conduct online classes and we are giving you some numbers, You can also make some complaints, some sort of clarifications may be made, communicated through the WhatsApp numbers given to you, provided to you. So with this, we come to the end of which is produced by the Media Division of Dhanamajuri Community College. Stay home, stay safe. Thank you.